Download this code from codegive.com, link in the description below. Decoding Endianness, a comprehensive guide to little-endian versus big-endian. Endianness is a fundamental concept in computer architecture that describes the order in which multi-byte data types, like integers, floating point numbers, and even strings in some cases, are stored in computer memory. Understanding Endianness is crucial for low-level programming, network programming, and data serialization/deserialization. This tutorial aims to provide a detailed understanding of Endianness, exploring the differences between little-endian and big-endian, their implications, and how to handle them in code. 1. The problem: multiple bytes, one address. Imagine you have a 32-bit integer, let's say 0x12345678. This integer comprises 4 bytes, 0x12, 0x34, 0x56, and 0x78. Now, consider that computer memory is organized as a linear sequence of bytes, each having a unique address. The question arises: in which order should these 4 bytes be stored in memory starting at a specific address, say 0x1000? This is where Endianness comes into play. 2. Big-endian, most significant byte first. In a big-endian system, the most significant byte, MSB, of a multi-byte data type is stored at the lowest memory address. Think of it as reading the number from left to right, just like how we typically read numbers or text. Using our example integer 0x12345678 stored at memory address 0x1000 on a big-endian system, the memory would look like this. Address value explanation. Dash 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 dash. 0x1000 0x12 most significant byte, MSB. 0x1001 0x34 second most significant byte. 0x1002 0x56 third most significant byte. 0x1003 0x78 least significant byte, LSB. 3. Little-endian, least significant byte first. In a little-endian system, the least significant byte, LSB, of a multi-byte data type is stored at the lowest memory address. This is the reverse of big-endian. Using the same integer 0x12345678 stored at memory address 0x1000 on a little-endian system, the memory would look like this. Address value explanation. Dash 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 dash. 0x1000 0x78 least significant byte, LSB. 0x1001 0x56 second least significant byte. 0x1002 0x34 third least significant byte. 0x1003 0x12 most significant byte, MSB. 4. Key differences summarized. Feature big-endian little-endian. Dash 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 dash. Byte order MSB at the lowest address LSB at the lowest address. Readability more intuitive, left to right, less intuitive, right to left. Debugging easier to read memory dumps harder to read memory dumps directly. Processing potentially faster for some algorithms potentially faster for other algorithms. 5. Why does Endianness matter? Asterisk portability asterisk data written on a big-endian system may not be directly readable on a little-endian system and vice versa. This can lead to unexpected behavior, data corruption, or program crashes when dealing with asterisk network communication asterisk network protocols often specify a particular Endianness, usually big-endian, often referred to as network byte order. Asterisk file formats asterisk many file formats specify the Endianness in which data is stored. Asterisk data serialization. Asterisk converting data structures to a byte stream for storage or transmission needs to account for Endianness. Asterisk low-level programming. Asterisk when working directly with memory addresses and hardware, understanding Endianness is essential. Asterisk debugging. Asterisk identifying and fixing Endianness related bugs can be tricky, especially when the issue arises indirectly. Example: a library handles Endianness without explicitly informing you. 6. Detecting Endianness. You can detect the Endianness of a system programmatically. Here are code examples in C and Python. C**. Explanation, C. 1. Unsigned int I equals 1, we initialize an unsigned integer I to the value 1, which is 0x00000001 in hexadecimal. 2. Char*. C equals, char, and I, we create a character pointer C and point it to the address of I. A character pointer accesses memory 1 byte at a time. 3. If, C, we dereference the character pointer C. This reads the first byte of the integer I. 4. Endianness check asterisk. If the first byte is 1, i.e., 0x01, it means the LSB is stored at the lowest address, so the system is little-endian. If the first byte is 0, i.e., 0x00, it means the MSB is stored at the lowest address, so the system is big-endian. Python asterisk. Explanation, Python. 1. Import sys, imports the sys module, which provides access to system-specific parameters and functions. 2. Sys.byte order, this attribute of the sys module directly provides the byte order of the system as a string, little or big. 3. Conditional print asterisk. The code then prints the appropriate message based on the value of sys.byte order. 7. Converting between Endianness, byte swapping. If you need to exchange data between systems with different Endianness, you'll need to perform byte swapping, also known as Endianness conversion. This involves reversing the order of bytes within a multi-byte data type. Here are C and Python examples. C. Byte swapping functions. Explanation, C. 1. Includes stdint.h, includes the standard header file for fixed-width integer types. Using uint16_t, uint32_t, and uint64_t guarantees the size of the integer, regardless of the architecture. 2. Swap_uint16, uint16_t val, swaps the bytes of a 16-bit unsigned integer. It uses bitwise left shift and right shift operators to move the bytes and then combines them using the bitwise OR operator. 3. Swap_uint32, uint32_t val, swaps the bytes of a 32-bit unsigned integer. It's a bit more complex, requiring shifting and masking to isolate and rearrange each byte. 4. Swap_uint64, uint64_t val, swaps the bytes of a 64-bit unsigned integer. The byte swapping is done using a sequence of shifts and OR operations. This is a more efficient way to swap bytes than swapping them one by one. 5. Main demonstrates the usage of the swap functions. It initializes sample values and prints the original and swapped values. Python, byte swapping with struct module. Explanation, Python. 1. Import struct, imports the struct module, which provides functions for packing and unpacking data into byte strings according to specified formats. This is the preferred way to handle Endianness conversions in Python. 2. Struct.pack, format_string, data, packs the data into a byte string based on the format_string. The format_string specifies the data type and Endianness. Asterisk, big-endian. Asterisk, little-endian. Asterisk I, integer, 4 bytes. Asterisk F, float, 4 bytes. Asterisk Q, long, 8 bytes. Asterisk H, short, 2 bytes. 3 struct.unpack, format underscore string, packed underscore data, unpacks the packed underscore data back into Python data types based on the format underscore string. It returns a tuple containing the unpacked values. The 0 at the end extracts the first element of the tuple, which is the converted value in our case. 4 swap underscore endian, data, format underscore string, function. Packs the input data according to the provided format underscore string into a byte string. Unpacks this packed data immediately back into its original data type. This ensures we have the correct representation of the data before swapping. Swaps the endian indicator, to or vice versa, in the format underscore string. Packs the unpacked data again using the swapped format string. Unpacks the newly packed data. This gives us the final result of the Endianness conversion. 5 built-in methods provides the simplest method to do the endian swap. Struct.pack, I, value, this packs the integer value into a byte string using big-endian byte order, and unsigned integer format, I. Struct.unpack, I, packed, 0, this unpacks the packed byte string back into an integer using little-endian byte order, and unsigned integer format, I. Important considerations asterisk. Asterisk network byte order asterisk most network protocols use big-endian as the network byte order. Therefore, when sending data over a network, you may need to convert your data to big-endian before sending and convert it back to the native Endianness after receiving. The socket module in Python provides functions like socket.hnl, host to network long, socket.entall, network to host long, socket.hns, host to network short, and socket.entos, network to host short, for this purpose. C also offers similar functions in arpa/inet.h, hnl, entall, hns, entos. Asterisk data alignment asterisk Endianness is closely related to data alignment. Proper alignment can improve performance, especially on architectures where misaligned memory access is slower or even causes errors. Asterisk Endianness is architecture specific asterisk the Endianness of a system is typically determined by the CPU architecture. Common architectures and their Endianness. Asterisk little-endian asterisk x86, x86-64, most common PCs and servers, ARM, typically configurable but often defaults to little-endian. Asterisk big-endian asterisk PowerPC, some configurations, Spark, historical, older Motorola processors. Asterisk by-endian asterisk some architectures, like ARM, can be configured to operate in either little-endian or big-endian mode. 8. Practical examples. Let's consider some practical examples where Endianness matters. Asterisk reading image files asterisk many image formats, example TIFF, store pixel data in a specific Endianness. If you're reading an image file and the Endianness of the file format doesn't match your system's Endianness, the image will appear corrupted or distorted. You'll need to perform byte swapping to correctly interpret the pixel data. Asterisk network packet processing asterisk when processing network packets, you need to be aware of the network byte order, big-endian, and convert any multi-byte fields, like port numbers or sequence numbers, to your system's native Endianness before using them. Asterisk database interoperability asterisk when transferring data between databases running on different platforms, example a database on a big-endian server and a database on a little-endian server, you need to handle Endianness conversions to ensure data integrity. 9. Best practices for handling Endianness. Explicitly specify Endianness when defining file formats or network protocols, clearly specify the Endianness of multi-byte fields. Use libraries that provide Endianness conversion functions, like the struct module in Python or arpa/inet.h in C, instead of implementing your own. This makes your code more portable and less error-prone. Document your code. Clearly document any Endianness conversions that you perform in your code. This makes it easier for others to understand and maintain your code. Test thoroughly. Test your code on both big-endian and little-endian systems to ensure that it handles Endianness correctly. 10. Conclusion. Endianness is an important concept that developers should be aware of, especially when dealing with cross-platform development, network programming, or low-level system programming. Understanding the differences between big-endian and little-endian, knowing how to detect Endianness, and using appropriate byte swapping techniques are essential for ensuring data integrity and portability in your applications. By following the best practices outlined in this tutorial, you can effectively handle Endianness in your code and avoid common pitfalls. Remember to always document your code and thoroughly test it on different Endianness systems.